Hi, everyone. My name is Marianne, and I am responsible for the training coordination at Hardent. I'd like to welcome you all to our webinar on how to use the Versal ACAP programmable network on chip. We're pleased to see that so many of you are able to join us today. I'll shortly be passing over to our presenter, Rick Eggleton. Rick will present for about 15 minutes, and then we'll wrap up with some of your questions. This is a great opportunity to ask him anything you've ever wanted to know about the Versal ACAP NoC. Please go ahead and submit your questions throughout the webinar using the questions box. Rick will then answer as many questions as time permits. If we don't get to your question, we'll follow up with an answer by email as soon as we can. I hope you'll all enjoy, and I'm now passing over to Rick, who will begin.
Good morning, good afternoon, and good evening, everybody. As discussed, my name is Rick Eggleton. I am a FPGA specialist for Hardent, and we are talking today about how to use the Versal ACAP programmable network on a chip. And this is all part of our new Versal technology known as ACAP. So Hardent itself, I'll just give a brief introduction to Hardent so you know who they are and I am at that point. So Hardent is we're a company, a consulting company located in Montreal, Canada, and we've got a very comprehensive portfolio of services and products that we offer to the outside world. And the intent there is, of course, to help customers optimize their designs, work with experts in areas that they either may not have an expertise or are looking for sanity checks or further improvements on what they're trying to accomplish. And what we do are design services from many aspects, from either A to Z, if you need a complete design done and not necessarily even knowing where to begin, versus maybe you only want a small portion where you don't have the expertise or that expertise is busy already and you're looking for somebody to come and fill in. So that's the design services side. We have IP products, of course, IP products that we go off and sell. Some of them are available directly through Xilinx, as we're partners with Xilinx. And we've also got training, which is part of what we're talking a little bit about today with respect to how to go off and use something brand new to the market called the NoC, the network on a chip. We have been certified members with the Xilinx Alliance program and also authorized training partners with Xilinx since 2009. So we're in our going into our 13th year now, as a matter of fact. Pretty much, you know, we've been working with Xilinx for a very, very long time. And, you know, Xilinx has recognized us as ATP of the Year a couple of times with the awards. Our trainers themselves have been recognized as top trainers for several years running across multiple years as well. So we, you know, we are very close to Xilinx, and we know a lot about Xilinx and how to go about using these things. Personally, again, my name is Rick Eggleton. I am based in Ottawa, Canada, and I'm an FPGA specialist and been here with Hardent since 2019, so I'm in my third year. Part of my role as an FPGA specialist is to help develop and customize material for the training program at Hardent. You know, and to look at it, some of the more unique courses that I've developed, I guess, since I joined include an advanced hardware debug course that talks about how to characterize your gigabit transceiver channels, and also how to use ChipScope Vivado logic analyzer, and actually you're able to target hardware that resides in Montreal to go off and do that performance in the course. We've got you know, a lot of new Versal courses that we'll talk about at the end of the session that we deal with, including some courses that we've broken up to be more dealing with the architecture, that are more focused on either the PL developer or the FPGA designer, the ACAP designer, versus an embedded designer. And also we have some exquisite time enclosure courses that are very specific to Hardent as well. So, you know, my experience, the relevant experience, I guess, is I had spent 15 years as a Xilinx FE dedicated to Xilinx global customers. That was my role, was the top 11 customers inside of Xilinx, specifically servicing around the Ottawa area, but stretching out beyond that as well as 4 years designing OFDM, which is pretty much everything that we do in wireless, or at least the key parts of wireless today, before OFDM was actually cool. So that's dating myself a little bit, but yeah, that's how far back I go. So for the most part, we'll get into our discussions, and Xilinx went off and they decided that they've gotten to a point now where an FPGA is no longer an FPGA. An FPGA, they designed the first FPGA almost 40 years ago. And what was the original intent and use of what that FPGA was 40 years ago was nowhere near what it is today. And with all the developments, the numerous developments that have occurred over the decades, it became prominent. Right? It became necessary for them to go off and change the name. It is no longer an FPGA or just an FPGA. It is so much more than that. So they've gone off and they've created something called an ACAP now. That's the new acronym rather than FPGA, which stands for Adaptive Compute Acceleration Platform. And that platform is where we are today with the Versal technology. It is intended for a heterogeneous acceleration, not solely just a hardware acceleration at that point. It's intended for any application and for any developer. So if you're a hardware developer, you've got the PL fabric there. If you are an AI ML type person, you've got the AI engines. If you are a software embedded person, you've got the processors that are there. It was developed and released on the TSMC 7 nanometer FinFET process, which is pretty much the latest, greatest as we look at it today. And again, it allowed for the software programmability and the more domain specific hardware acceleration that, because it is FPGA based, if we want to look at it that way, it has that adaptability wrapped around it. It means that, yes, there's a lot of hard macros in here that have a tremendous amount of flexibility as well as much, much more. When Xilinx released the ACAP at Versal, they talked about, at this point, 3 different pillars or 3 series of devices that was announced. And the intention behind that was for scalability and AI inference, moving forward towards what is more necessary towards the application that I'm targeting. I don't necessarily need everything, and they try to break that up as they always have in the past. There's the 3 basic pillars as we work our way through. There's the Prime series, which would be the more basic series at that point, which has the DSP engines. It has the logic cells, the lookup tables, the serial transceivers. So the basis of all 3 families is pretty much the same. They all have DSP engines and general fabric and ultra RAM and block RAM and serial transceivers and processors in the ARM72s, et cetera, as they work their way through. The biggest difference is the mix that kind of goes into those. You can see that in the Prime series, you've got up to almost 4,000 DSP engines versus the Premium series that's got superior to 14,000 that are available. So these are really high bandwidth capable parts. They are very comprehensive in what they're able to do. The biggest difference, of course, that helped turn this into an ACAP as well is you've got this AI engine that's part of the core series, and the core series only at this point. And there's a matrix of between 128 to 400 of these core AI engines available that, to look at it, I guess, it's kind of a, to put it simplistically, I guess, it's a math engine on steroids. And it's not part of what we talk about today, but there are numerous courses, classes that are available to go off and learn about it, as well as some upcoming webinars. So to take a step down from that 100,000 foot view to 20,000 foot view, if you go in and look at it, each and every one of the parts is going to contain everything except for the AI engines, and that's only the core series that has that. So you've got your scalar processors that have that ARM dual core next generation A72 that goes along with it, as well as that dual core Cortex R5. You've got the general fabric that has been, the mainstay of Xilinx for, again, almost that full 40 years, where, from 40 years ago, there was no block RAM or ultra RAM or some of the other macros that were involved in it. It was lookup tables and flip-flops and a carry chain, but it's so much more than that that turns it into an ACAP. There's also the adaptable engines. There's of course, the AI engines, those math engines on steroids, as well as DSP engines. And it's a bit of a misrepresentation to show that the DSP engines are kind of relying on their own. It is part of the intelligent engines pillar, if you look at it that way, but they are still part of the general fabric. It's where they've always been and will continue to be. Within that, of course, are all the different macros that are available for you to go off and do different communications, including PCIe C6, Ddr master controller that is very tightly integrated into programmable network on a chip, HBM, 600 gig cores, etc., depending on the part that you're buying. And then the 28 gig, 58 gig, 112 gig capable gigabit transceivers that are available for you. So there is a huge copious amounts of bandwidth that can move through these devices. And it became evident that just moving this through the regular fabric was doing a great disservice to what the capabilities of the part actually were, and being able to move between the different pillars. So between the processing system and or the general fabric and or the AI engines, it became important to be able to get the data there as quick as possible. And Xilinx, along with the AI engine, created something called the programmable network on a chip that's now part of each and every FPGA that goes out in the market, or each and every part of the ACAP that goes out in the market today. So with respect to the network on a chip, there are definite benefits that go along with that. First and foremost, it is fast. It is extremely high bandwidth for moving huge amounts of data, copious amounts of data between the different blocks within the ACAP. It's got the NoC that is very, for moving that data around, and that's again what today is about. You're moving huge amounts of data in and out very quickly through all the different pillars, as well as across the outside world as well, as it connects up to a lot of the major blocks in I/O that connects to the outside world. You've got a tightly integrated DDR master controller that's available, and part of it and connected, as I said, very tightly controlled to the NoC. It can do DDR interleaving, and to get away from bottleneck management, how to go off and work with that. That's why they went off and created that specific block that's there. And a key thing to understand is this is, although it's programmable, it is flexible, it is hardened, it is there on the device. So in order to be able to move copious amounts of data very quickly, this was hardened. This is a macro that's put down into the device, and one that you need to be able to move to get across to the different areas that are there. So because it is a silicon implementation, it meets timing. What are the specifications? You turn it on, it meets the timing. It consumes less power because it is built to do this purpose, so you're doing less power. And there is no PL routing resources once you get off and into the NoC. At that point, you are solely off in that domain, which can save you a tremendous amount of cost to your design at that point. Some of that cost might be speed, it might be power, it might be many other things. So like most macros that you create inside of an FPGA, it's built very specifically to do things. So again, if you look at the way this works, you've got your NoC that kind of moves the data around the NoC, as we look at it that way. And you've got AXI interconnecting network that either comes out of the programmable logic, out of the AI engines, out of the PS, that goes off and it communicates through these master units that ultimately get it out onto the NoC, onto that network. And it is received at the other side of the network, wherever it needs to be used, again, whether it be in the PL or in the DDR or in the PS or in the AI engines. It has a slave unit to get it off that as well. So it is, again, a dedicated switching up to over a gigahertz. So the vast majority of parts that Xilinx is putting out there right now will be a gigahertz or more. And again, is using AXI to get on and off the network at that point. And again, it's a very high-speed hardened data path that is correct by construction. It is intended to work at this rate and will work at this rate. And then it's up to the designer to make sure you're doing the right things to use it appropriately. So the NoC is basically made up of a southern path, the horizontal on the southern, which has 4 channels of 128 bits that are running across it. There's the northern path as well, the horizontal there, that is 2 128-bit paths that are running through it, and then a number of verticals, from 1 up to 4 verticals that are running 2 vertical paths at that point as well. And again, they tightly coupled down to the DDR4. And in order to go off and use this, again, this is a hardened macro. And if you are using the NoC, you need to go off and use it, and you would be configuring it via Vivado IP Integrator tool, which some or all of you may have used and some may not have used. This is what our demo will be when we go through it in a little bit here. So for the most part, you've got these horizontal and vertical paths that are, again, in silicon. They are built to be this, therefore they will run at these speeds. You've got the bandwidth available to you, it's what you do with it. So part of the NoC, as we as we work through it. So you've got the network on a chip, again, with the horizontals as we look at the yellow lines, and the verticals as we work our way through. Again, built to be up to 1080 megahertz or 1.08 gigahertz capability across that 128-bit channels, and 4 channels on the bottom, 2 channels at the top, 2 up the verticals. So from there, you've got the NMUs, the master unit. And the master units, this is where you put the data out into this super highway. This is the on-ramp to that super highway. So you would be delivering from the programmable logic or other areas that are available. So the AI engines or coming out of the DDRs or the PS, you would be entering it by going AXI interface to the NMU. The NMU then would go off and create packets at that point, put them out into the bus. I'll talk a little bit about that in a minute. To get off the highway, you've got the slave units, and the slave units, again, not just in fabric, it's also in the PS and in the AI. Again, you've got these specific macros that are built into certain areas of the FPGA that you would communicate with in those large pillars of area, being general fabric, being programmable logic, again, the general fabric, the PS or the, which is the processor subsystem, or the AI engine matrix. Between those NMUs and NSUs are multiple areas where there are packet switches. And the packet switches allow you to be able to move either across the horizontals a certain number and then come down whatever vertically you need to, and try for the compiler to pick the best path to be able to arrive from your source to destination in the required latencies, which you as a designer would go off and set. So you've got the masters, the slaves, and the packet switches. There's also this inter-die bridge if you're in one of the devices that has that's part of the stacked silicon interconnect. So you've now got these high-speed lanes that move between the different monolithic die that reside under the hood of the ACAP at that point, as well as that tightly coupled to the NoC, that Ddr Memory Controller, and again, multiple of those, between 1 and up to 4 of those, depending on the part that you're targeting and what's available in it. So again, I talked about turning these into packets. So you would deliver the data into a master at that point, and the master would then packetize these, create this packet of information that's known as a flit. So a flit is 128 bits wide, so it's the width of the channel, and 1 bit deep at that point. And within those flits, you would pack either data or overhead, depending on what you're trying to accomplish. So it's actually flits that are moving at that gigahertz, running through the NoC fabric at that point from whatever domain that you are coming from, whether it be PSPL or AI. So just to get a little bit, better idea of how it actually works. So here we've got the master. When it requires a read, it sends a data flit to wherever the slave resides. Once the slave receives that, it then turns around and says, okay, sorry, an overhead flit, a header flit, an overhead flit to the slave. The slave says, okay, what do you want? Now it turns around and says, okay, I understand what you want. I'm going to send all this back. And this could be 1 to many data flits as it works its way through. So all the information in the NoC, it moves ultimately as flits. And these can be data and or control or overhead. And it's 1 pathway wide and 1 cycle. So it takes a flit, takes 1 cycle as it moves from the master to the packet switch, and from packet switch to packet switch, and or packet switch to the slave unit at that point. So you can very rapidly get an idea how long is my static path at that point. It can also do quality of service, which we'll spend a little bit of time later on discussing, not in deep level, but just get an idea what's available. And the whole point of that is it's not just moving a flit across the whole thing, it's ensuring the right flit movement. Is it going to the right place? Is it given the right priority to move around? And there's also the compiler, which is part of the IPI discussed already. That's what gathers the connections and the configurations of what the designer wants. And then it's based on what the designer describes to it, just like it does in FPGA or other things that we do as design. It gathers the connections, configurations, and it creates these attributes and settings for the NoC. And remember, the NoC is a hardened macro. It's not, some of this is here now and some of it's not because I'm not using it. It's there. It's how you use it. And that's what you're describing, or letting the compiler describe to you at that point, is how to go off and use these things. So again, it outputs a hardware description file that would be included, as it's no longer a bit stream anymore. It's much more than that. So part of what that much more than that is getting this NoC attributes.dat file, that there is a NoC in every single ACAP. So there will be a DAT file associated to every single ACAP that you create going forward. So as a fairly generic example, we look at it here, we've got whatever is delivering the data at that point. So whatever the source of our data is. So it's processors, DMAs from the outside world, input input devices, other input devices, IP in the PL or the AI engines. That is connected up to the NMU through AXI or AXI streaming. The master at that point now packetizes, creates the flits, and starts, defining how the flits need to move. So the flits, the path is already defined. It's when it leaves at that point based on some of the priorities already set. As I talked about, the routing is already kind of predefined at that point. We know how many packet switches we're going from. We know where we're starting and where we're ending. So that path is already defined at that point, and the compiler, and we've agreed with it as designers. It moves its way through the routing and ultimately ends up at the slave unit, and that is where it depacketizes the data, moves it back to whatever domain we need to be capturing it in. And again, that's the processor, the DMAs, inputs, the PL, or the AIEs, whatever it might be. So that is a fairly simplistic view of it as we work our way through, but one of the things you might actually glean out of this is that the NoC master and the slaves, they are actually fully responsible for the clock crossing domain between those 2 points. And it is handled seamlessly for you. You don't need to worry about it. So no matter what the rate is on this side, it will translate it into that gigahertz or faster for the majority of them as it works its way, as the flits work their way through the device. So again, from a features and performance perspective, the intent is to move data very quickly, very efficiently. So it also enables the sharing of some of the limited amounts of hard IP that you've got out there, whether they be memory controllers or other type of IP, including I/O, and as well as between the user IP and the PS and the PL and the AI engines, whatever it might be. So a big part of what you're going to be looking at is, of course, the resource savings that come along with this. You no longer have to route all these different engines through the PL anymore. You have to route them through the PL to get to the NMU, but you don't have to cross the device or other things that might be going on in order to be able to move data either from the PS or to the AI engine, or even from PL to PL at that point. So you get lower power and a higher system throughput by going off and using the NoC. So there's an example here where they're designing a few traffic generators, and the interconnect associated to those, as we look back to the traditional way of how we used to do this in FPGAs in the fabric there. So for the most part, if you look at the total number of traffic generators and the interconnect associated to them, it took quite a few resources. So the total resources were 70K LUTs and 70K flip-flops, where the interconnect itself required more than half. It required 37K lookup tables, 42K flip-flops. So by going off and now targeting this to an ACAP instead, now you can use the NoC. And the benefit of the NoC is you don't have to do a whole lot of what's actually going on in order to move that interconnect through. So the total resources drop by pretty much 50% from a lookup table perspective, 60% from a flip-flop. And when it comes to the interconnect, there's no resources. It is only using the NoC. And the NoC at this point would be both the vertical and any horizontal that would potentially be required, depending on how you're getting on and off that superhighway. So again, there is support for quality of services and virtual channels. There are up to 8 different channels virtual channels for every physical link. So you can have multiple masters driving through the same paths if you want at that point. And each of those would have their own physical links and or virtual links, and you would use the physical links that are available to kind of work with, and you would run your way down the virtual that way. The intent of this is to help balance the latency and bandwidth requirements, because not everything can be the most urgent at that point. So yes, there are decisions that designers have to feed to the tools so they can make decisions on how to start planning these things out and creating the routes that are taken and how often these routes are available and how much data bandwidth one engine gets versus the other engine. So the whole intention there is to ensure timing of the higher priority data and allowing the rest of it to kind of fit its way in there. And we talked about how many lanes there are in the horizontals and the verticals as we worked our way through. Well, each of the lanes are fully independent, and there's a maximum bandwidth per lane, of course, and 1 gigahertz being, let's say, the average, but at 1080 megahertz, 128 bits, that gives 138.24 gigabits per second. So that's per lane. Remember at that point. So that's a significant amount of bandwidth that's actually available for you to move data through the device. So there are different factors that affect the system performance. There's the traffic class that specifies the priority of the packet as it's working its way through and making sure that which one is treated with higher priorities than the other. There's the bandwidth, of course, which is how much data gets through in an average amount of time, whatever that unit is that you use at that point. And the latency, of course, is when I first deliver the data at the master and when does it show up at the slave at the other side? What's the total latency through there? Because all of these are important factors when we're going off and trying to define our system performance. So there are three classes as we work our way through. There's the low latency, which is the higher priority, isosynchronous, which is in the middle, and isosynchronous meaning occurring at the same time. So occupying equal time, everything always takes this amount of time. And then there's best effort, which is everything else, not the highest priority, doesn't have a priority really at all. It's fitted in when you can fit it in, which expectantly you're managing as a designer to make sure that it can actually fit. So the different classes, of course, are at a low latency side, that is your highest priority. So it minimizes the structural latency at bandwidth at that point, but it's only applied to read traffic when it's just data overhead, or not data, when it's overhead at that point, control overhead. It doesn't necessarily require the same priorities. With respect to isosynchronous, again, same time, right? This is where you go in and it guarantees a maximum latency. And it assigns a medium priority at that point. So your low latency on reads is going to get the highest priority. Outside of that, well, now we start looking at the isosynchronous. When we get down to the best effort, it's literally that. How much bandwidth is left over? And yes, it's up to the designer to make sure that there is going to be enough bandwidth left over that ultimately things are going to be serviced and they're not ultimately starving to get data or information at that point. So to turn around and look at it here, if you look at one lane, your total bandwidth would be 16 gigabytes per second, 128 gigabits per second at a gigahertz, right? As we work our way through. So your total bandwidth is 16 gigabytes per second. So if you've got one master and only one master using those paths, therefore, or one that only wants to use it, it's got the full 16 gigabytes available to it at that point. But if you've got two that want to use it, then you're going to have to decide which one gets a higher priority, which one gets more bandwidth. And if you don't, then they're going to be balanced, and it's going to turn around and say my master A and master B, they each get half of that bandwidth at that point. And again, as you work your way through to more and more masters sharing the same routes, the same paths, then you need to define to the tool, because the tool doesn't make up its mind, but you would define to the tool what the bandwidth, what the priorities are. And yes, the tools, there's a lot of things that they try to do, but it doesn't necessarily understand your specific needs around your design. So you need to have very specific input into the device, into the needs of the device, to make sure that things are happening in the time that you want it to occur, so that you can go mission mode into the field and have things work. So typically when you kind of look at it here, it's always good to have a little bit of unused bandwidth as well, in order to give an opportunity for burst transactions to have it no matter what the master is, and try to give it a little bit of room. So typically that's the way that it works, but you should know your needs, your specific needs for your product better than we would. You make those decisions as to whether you even have unused bandwidth or how much you would need to allot for certain burst sections, and how often do you expect bursts, et cetera, as you work your way through. So looking at performance metrics when you get into latencies. So here we've just basically chosen some programmable logic IP that goes off and talks to some programmable logic IP on the other side of the device. So this is a fairly long path where you've got 12 packet switches. If you count them through, you'll find that there's 12 packet switches. You've got the NMU where it hops on and the NSU where it hops off. So at 2 clock cycles per node, if you want to work your way through there, that creates a minimum latency of 28 clocks. That's assuming it's got full path, there's no virtual channels interfering with it or anything of that sort. Full path takes 28 clock cycles. So this path works really well if your latency requirement on your design is 30 clocks or more. And if it's not, maybe 36 clocks isn't enough based on how many things are actually sharing that path. It's up for you to try to work with the information to make sure that you're getting enough that's coming out of there. So if it finds that it's not enough time, then the NoC compiler, it's going to look for alternative paths to go off to do. And maybe if it just can't get here in time, you've got to take a step in, as we do as normal FPGA designers or software designers. We will always have our brain, will always be smarter than generic heuristic algorithms that were written by somebody that resides, I don't know, in Colorado, right? Trying to define how the heuristics should work in generic cases. So for the most part, you should know your design better. So further guidance such as floor planning might be required for you to go off and create a shorter path for it to go off and get what you want to get. So, and more than anything else, you want to make sure that you're specifying a latency that doesn't over constrain the design or become your real first, your first order issues, such that the tools are spending all this time and just can't get here from here. Make sure that things make sense. It's precise and pristine when you deliver your design constraints to your design. Make sure that you're doing the same thing with the latencies as you work your way through. So again, when it comes down to latency, there's two types that we're kind of dealing with. There's that structural latency that we talked about, where we had our 12 paths that we potentially worked our way through. And again, maybe we went off and decided I want to lock things a little bit closer such that I can now, I don't have to go through 12. I'm only going through 1, 2, 3, 4, 5 at that point. So we saved ourselves seven packet switches or 14 cycles to get there. So again, you've got the structural latency, which is it's going to take at least this amount to get through no matter what else is going on. But then there's also queuing latency that you as a designer will have control over. And that queuing latency is dealing with things like virtual channels. So which are my higher priorities? My channel 1 and my channel 4, my higher priorities. Everything else is either isosynchronous and or best efforts as we work our way through. All that plays a role in as to how much queuing latency is going to be involved in what we're trying to do. So that structural latency of 28 cycles, now you start adding some virtual channels in and queuing latencies, et cetera, that can very quickly become 30, 40, potentially even 50, depending on priorities that you give things, cycles of latency before the data can actually start arriving. So talked about the NoC and the DDR, being tightly coupled at this point. So they're, within the AXI NoC, we're not specific to this, but we do look at it a little bit in the demo. We go off and we look at this, we say, okay, like any other IP that's inside of the that's inside of Vivado or inside of Vitis at this point, you've got access to the IP catalog to go off and define these things. So in our case, we're looking at a memory controller, which is part of an AXI NoC. We say that it is a controller type, and you can select either DDR4 or LPDDR4. And again, you can get superior to 4 gigabits per channel on a regular I/O. When you're looking at it as you work your way through these things. So the regular I/O is extremely capable of doing, what we looked at 20 years ago as being a high-speed serial I/O gigabit transceiver. Just the regular I/O inside of the Xilinx I/O banks at this point can do better than what the first couple of generations were able to do. So you would go in and you would open it up like anything else in IP catalog, and you would start defining what your requirements are as you work your way through for that memory controller, and then you would connect it up as you so need, whether it be AXI across the NoC or other ways of going off and doing that. Now, we talked about the DDR memory controller. There's a lot of different DDR4s or LPDDR4s that this can connect up to. Make sure you understand which one that you're actually going off and connecting up to. The definitions are always typically in the name and the way that they go off and work. And you're looking at pretty much, what's the row address bits, the column address bits, the bank groups, and any other information that you can fit down in the last few bits that are available for you. And one of the other questions that comes down is, of course, debugging. So yes, the vast majority of debugging kind of relies on us as designers to make sure that we're putting something together that's actually sane. We want to make sure that it's usable, that it's sane, that it has a chance to do what our system requirements are actually requiring at that point. So, the designers play a very key role in making sure that we're not trying to do something that just you can't get there from here. It's not possible. But with that said, a lot of the times we're letting the compilers go off and try to give them as much freedom as we can before we start restricting and figuring out other things. So the compilers will come back and they'll tell you, based on the information, so garbage in, garbage out, or pristine information that we've given it, you're going to get some information out the other side, and that information is going to define to you, what do I need to do next? Oh, I pass and everything is copacetic. Great. That's assuming you're precise and pristine in constraints. Everything should work perfectly well. Whereas if it comes back and starts complaining about certain areas, well, there are ways to improve traffic efficiency. So you might want to examine what are the shared routes to the NoC? Do I have too many key masters that are sharing the same paths? Maybe I can change some of the areas that they come in at that point. So again, identify the masters using a very limited resource at that point. So again, yes, there's some very high-speed lanes that are through this, but at most there's 4 on the lower horizontal NoC, and versus 2 on the upper NoC, and the verticals are horizontal, the upper horizontal and the number of verticals. There's only 2 paths in there. So yeah, they're fast. They can move copious amounts of data really fast, really hard, but if you're trying to put everything into the same channel, that can be problems. We talked about earlier, maybe you move the master closer to the slave, or maybe you give it more, for the higher priority ones, the ones that are really critical, give it more bandwidth allocation for that path. So yes, some of the other ones might be cut down a little bit, but if they're not as critical, that's okay. Or reduce bandwidth on other best effort masters at that point, so that when they do get access to it, they're not pushing a whole lot out of there. They're kind of pushing some, backing off, and looking what else needs it, and then going and pushing others. So, and maybe you increase traffic class to isosynchronous rather than best effort to give it a little bit, stop it from starvations or other things as we work our way through. So that's pretty much what the presentation is about. I'll get into a demo talking about how to go off and actually use the NoC at that point. So again, IP Integrator becomes necessary in every design that's using ACAPs at this point. And the reason being is, that is the compiler for the NoC at that point. So there's a lot of people that either don't know what IP Integrator is, never used it, been intimidated by it. I'm hoping that by going through the demo a little bit, you'll, it's going to release a little bit of the stigma, build your confidence in going off and using it, because it's really quite straightforward and quite simple to go off and use. So I'm going to break for a few moments here, and we'll get off and we'll do our demo. So what I've done for our demo is I've used the first lab in one of the courses that we have called the NoC Intro. I'm using the Xilinx Virtual Manager, the virtual machine, the 2020.2 one specifically, and that brings us up to here where we have where we're actually using that virtual machine. Inside the virtual machine, I opened up a terminal. Took us to the correct directories that we needed to be in, and these are the directories here that we're often using at this point. That's not what I wanted to do, I apologize. And ultimately, in order to save a little bit of time, I've set the environment up and made sure everything is working properly. And I've opened up the Vivado 2020.2 so we can go off and we can start using the Vivado specifically with the IP Integrator. So for the most part, I went to a support directory that holds a tickle script, and this tickle script is there. It's got some helpers that are there for this specific demo, that some procedures and so on that are there to make sure that we don't have to spend too much time setting everything up. So without further ado, we'll go on a little bit further from here and start actually using some of those procedures. So the first procedure we're going to do is we're going to set up a project. So we've got project create that's available for us that's actually going to open Vivado, and it's going to target the specific board and part that we want to be going off and using at that point. So it is very specifically, it's the VCK 190 is the part, and it's the VCK 190 evaluation platform. As we work our way through. So that is the evaluation platform. You can see a little picture of it here as we work our way through. And we've now opened a project specifically targeting that board. So this project has all the information as to what all the different peripherals are, what IO they're hooked up to, etc. From there, we want to be using IPI, so we're going to go in and we're going to do something called block design create. So we're going to now open up that project inside targeting that part using IPI or the block design at this point. So we get this nice empty little BD or block diagram that's fully available to us that, oh, look at that, it's got a picture of the NoC on that. So this is an empty NoC. This is what the hardware actually looks like. We talked about this being a mapped to the silicon. Yes, it's a high level look at it. It is obviously not perfect in the way that it shows it, but for the most part, you go in and you can see, okay, at the top level of this, these are, this is our horizontal 2 paths. This is our horizontal 4 paths that work its way through, and then our vertical 2, 2, 2, and 2. So this specific device, this is a representation of this specific device. It's got AI engines at the top, so it's got our slaves and masters connecting to those. We've got 4 verticals in this part, and every part's got at least 1 vertical. It's got the horizontal, and it's got the horizontal top and the horizontal bottom being with 4 lanes, 4 channels. So we've now set it up as a diagram, but it's an empty diagram. So instead of having to repopulate the world at this point, we go off and we can set up and do, start adding some stuff. So there's literally a command where we can go off, a procedure where we can go off and we can add stuff to the design. So we hit this, it takes about 10 seconds for it to go off and set everything up, and it starts adding very specific things. So it's a block RAM and controllers, and it's got the SIPs, which is the control interface processing system, the output to that, as well as the traffic generators that are available from Xilinx as well. And this kind of breaks them all up and puts them all there in the middle of the platform for you to go off and use. So we didn't have to create these. So I'm just going to clean it up slightly to show there's the controllers, a couple of block RAM controllers, a couple of traffic generators, and the SIPs block. So now we want to turn around and say, okay, I want to be doing some DDR4. So in order to use DDR4, I have to go get a NoC because that's part of the controller. So we get a NoC at that point. So I open up IP catalog, I type NoC into the search, and you can see there's multiple different NoCs. We talked about being the AXI NoC, which is memory mapped. We've got the streaming as well that's available for you, as well as some other NoCs. But for the most part, I double click on the AXI NoC. It's a memory map that I want to be going off and using at this point. It takes a moment for it to kind of go off and create, as IP catalog normally does, but it only, within 10 seconds or so, it kind of comes back and says, okay, here's your NoC. It's a generic NoC. It's not configured, but for the most part, we look at it, we click on it, highlight it. We can come in the properties window and we can change this name to be, okay, this is the one I want to connect to my DDR. And not only by name, we go into it now, open up the XCI file or the configuration capabilities of it, go into our general tab, and we say, okay, I've got one slave interface that's going to be communicating. So my processors are communicating to my DDR4, I've got a slave. I don't have any master at that point required, as I don't need to be talking to anything else, and I need a clock. Now, it is a memory controller, so I have to tell it, you are a memory controller. Is it interleaved by 2, by 4, whatever it might be? In our case, it's just a single memory controller, and it's going to have one port, which we could increase if we wanted. So from an input perspective, we go and look at this. Well, this is connected to the SIPs. It is not part of the programmable logic, the PL. So we know it's connected to the SIPs, and in our case, it's the PS, so we want it to be in non-coherent mode. We go off and we set that, and again, it's associated to that clock. Now there's outputs and connectivity and other things that we'll get into in a little bit, but for the most part, that is all that we need to set for this guy. So we just say okay, and it goes into the background and it configures it. So for the most part, we turn around and say, okay, because it's a memory controller, because it had that one interface, that's the processor, we can turn around and say, okay, now I want to be using IPI, I want to do some run connection automation at that point. Now it's only the DDR that I'm looking at. So I'm only going to select the DDR at this point. I haven't done anything with the controllers at that side. So I say okay to that, and it kind of goes off and it looks at, okay, what am I supposed to connect to? And it makes those connections. So I'm just going to regenerate my layout so it looks a little bit smoother. So you go, okay, there's my SIPs, it's talking to my NoC, that's communicating to the outside world with my DDR4. So this is exactly what we were looking for. Now we're going to start connecting up some of the others. So I can add IP. I can click the button up here as well. Add IP. I want to be looking for another memory map because I want to start working with my controllers and with my traffic generators. So I'm just going to clean this up a little bit more so I can make it a little bit easier for you guys to kind of see what's going on. But again, just clean it up slightly, and I'm just going to focus in on a different area in a minute. But for the most part, I'm going to highlight that new NoC. This one, we're going to call it, let's say, our traffic generator to our block RAM. So that's the controller. So the TGs to block RAM, very descriptive name. It says what direction things are going. So from there, see the name change, I double click on it, and I go in and I start adjusting what I want to start. So I go into the general inputs. This time, because I'm dealing with a couple of controllers, a couple of traffic generators, I've got 2 slave interfaces, I've got 2 master interfaces, and we're okay if it uses the same clock, no problem there. There's no memory controller involved in this. Although it's memory with the block RAM, it's not a memory controller, so we are not intercommunicating with the DDR4. Now, on the input side, well, we are connected to the PL. We are going from PL to PL. Our traffic generators are in the PL, that's okay. So we don't have to change anything here. Same thing on the output side, the slave side. We are connected to the PL, so we are going from fabric to fabric, but just across the chip in one manner or another, depending on what the requirements are. that we set and where we put things. Now we go to the connectivity side. So by default, it connects slave 0, master 0, and says, yeah, this is the communication path, which is perfect for what we want at this point. But what about the other interfaces? So we've got the ability to change this to whatever permutation we want. In our case, I'm going to look at slave 0, 1 going to the master 0, as well as master 1. And we can also go in and set quality of services if we want to, which is not part of this demo. We can set whatever we want at that point. We can create bandwidths that we want, adjust everything that we want. And of course, all this should have been mapped out by your systems guys and working in conjunction with your systems guys to know what your requirements are. Or you work your way through and try to find out, what does the tool do by default and what adjustments do I have to make? Because the defaults might be good enough. Those, that software coder for the algorithms that makes these generic heuristics for this part might be perfect for what you're trying to accomplish at that point. But for the most part, we've gone off and we've set everything that we want to set. We say okay, and that sets our IP in the manner that we want to go off and use it. So from there, we kind of look at this and say, okay, I'm just going to tie in a little bit closer. So it's kind of nice to be able to have this zoom capability. I tie in, and now I'm going to start making some connections. So I look at my traffic generator, put that down to the slave there. Traffic generator, oops, sorry, I want to make sure I highlight the right thing. Traffic generator 1 connecting to the slave of 1 there, and the master of the NoC going off to slave 0, and master 1 going off to slave 1. So now we've made some major connections. So literally in that amount of time, I have literally made a couple of hundred connections that we would have written in our HDL. And we can save a lot of time. It's also correct by construction because here I am connecting an AXI and AXI. The tools understand what these proprietary buses or non-proprietary buses are. They understand how to go off and connect these things. So it's looking at all the different connections and making all those connections. So we don't necessarily have to worry about that. So I'm going to pull back a little bit here, and I'm going to go back and say, okay, everything's connected. So now the tool should be able to figure out what a lot of the other connections are. So I go to all automation at this point, and I'm going to select them all because it's got my 2 block RAM controllers, it's got my 2 my traffic generators, both of those, and it knows how they're connected. So it's going to look at the rest of the signals and try to connect up as many as it possibly can, which it just did here. Now from there, it's not quite finished yet. I want to run connection automation again because I want it to take a look at the resets. And in our case, because I'm a designer, I know my design, I know that my reset, I want to hook it up to the SIPs and it's the active low because it's an AXI interface. I say okay to that. It goes off and does what it wants to do as well. And because Xilinx was really nice to us, we would have to go in and create a few more connections at that point. We go off and we finalize our connections by using one of the procs that they provided for us called the traffic generator enables. We go off, we click that, and it creates this constant to make sure that they're always enabled at this point. And so we've made all these connections. We can do kind of a review at this point, see all the different connections, the general clocks are being used, et cetera, as we work our way through. And that's the default view. There's a whole bunch of different views that you can potentially go down and look at that point, including an addressing view that kind of breaks things up a little bit more. And you see that, yeah, these are my major blocks that I was looking at before, and this is the way that they're being used. So I'll go back to the default view and I'll come back to the diagram. We look at our NoC and you look inside the NoC and go, okay, there's our basic NoC again. You can see, and you'll see in a few minutes, nothing is actually connected at this point. And that's okay. We haven't tried to validate the design. Once you validate the design, you're also trying to compile the NoC at that point, which we've not tried to accomplish because we've not quite finished everything yet. So we go into our address editor again, which is available here, and we look at this and say, okay, our DDR4, those addresses are very well known, but what do you want to do with these as a designer? So you can go off and you can create your master base addresses and et cetera, or you can right click and just tell the tool, go assign whatever you have to assign. And it goes off and it assigns different addresses and the ranges that it understands that you're often using at that point. And from there, we go back, we look at this and say, okay, everything's connected. It's all got its addressing, assuming I did my live demo correctly, because that always goes so well. I click on validate design or hit F6, and that goes off. And again, it reviews all the connections you made, make sure that they're sane and doing the things that they want to, and it goes into the NoC compiler and looks at all the things it's supposed to be touching and creates this design for you. So everything was kind of left at default. So it tells us our validation was successful, excellent. We go in and we look at it and go, oh, okay, well, this is what we expected from our diagram. There is our there's our SIPs block that's often talking to our through the NoC and often talking to our DDR4, and then our traffic generators that go down and talk to our block RAM. So they're all evidently here. And what's nice is you've got that color coding again, where you've got blue in this case highlighted deep in blue, and that's the path that it actually uses to get down there. So you can see, you can even click on it and you can see all the different paths that are available to it. So zoom in a little tighter there. If we look at our properties, that's our X0Y5 NMU. And it's 128 coming out of the SIPs. Same thing on the slave side of things. It's a slave, but it's a DDR MC. And as we go back, you can see that there are 4 controllers available for this. We look at the PL side of things, and it said, okay, you're using the master. You're using a master at that point. It's an NMU, and it's located at X3Y6. And X3Y5 for the secondary one. Look at the slave side. On the other side of the network, it's looking at the slave, right? NSU, it's a slave. So everything evident for you as well at that point. So that kind of brings us to the end of our demo. We're approaching some good a time at this moment. So we've actually done pretty good with the demo at this point. I will just minimize it, get it out of the way, and we'll come back to our presentation. So again, that's the demo. If we kind of look at what we've been talking about over the last 50 minutes, we've been looking at what is the network on a chip. So it not only moves the data within the device, but it's also very tightly coupled to the DDR memory, which at the rates that we're doing today, that's superior to 4 gigabits per second per IO. It's very important that you're able to, you're not a bottleneck internal to the FPGA. So the NoC helps get us there for sure. We talked about the key components of the NoC, which is the master units, the slave units, the packet switching, and of course the routing resources that tie all of these things together. We took a brief look at the quality of service for the 3 traffic classes that are available with the low latency, isosynchronous, best effort, as well as the 8 virtual channels that are available per packet switch as you work your way through. Beyond that, we also have beyond that, we've also got a definite increase in system integration. So it gives you that high bandwidth connections among all the major areas that you work with within the device. It no longer has to, you no longer have to create these long paths that are using very preferential routing inside of the FPGA to get from point A to point B inside of a constrained time as you work your way through. You've now got the NoC, this network superhighway that you can jump onto to get to other areas inside of the ACAP, so that you don't have to be using all those great routing resources and build yourself up from there. And again, saving power, giving better speed, et cetera, as you work your way through. So from there, we've got a few other webinars coming up for those that might be interested. So in June, we talk about understanding that AI engine, which a lot of people, this is again, one of the more significant parts of the ACAP is that created, why Xilinx had to go to an ACAP was the AI engine. So there's gives you, you get an understanding of what is an AI engine, and Reg will be bringing us that in June. Getting into July, we've got constraints management on Vivado. So how to be precise and pristine in what you're trying to create at that point, as well as in August and beyond. We try to do one webinar a month, go off and using this new Vitis platform that is, it's the direction of what Xilinx is going in the future. You've got Vitis as this superset of tools, which is now, what was SDK is now Vitis, as well as the what's under the engine under that is Vivado and HLS and a lot of other tools that are available to you there as well. For those that might be interested, upcoming, we've got some Versal ACAP learnings in June, July, and August. So, we created these very specific paths for an embedded processor or a programmable logic designer to get more focus instead of having this generic 3-day that talks about, both aspects of it. If you're more focused on one versus the other, you can get in there and talk about that. The programmable logic, that has, a lot more of the NoC information that I just talked about. There is a 1-day on the NoC, but all this material has been brought into the logic architecture as well as other material as well. And then you get into the AI engine, beginner, intermediate, and advanced. There's the FPGA design using Vivado, and these are our customized courses. So doing advanced XDC, static timing analysis, design methodology, advanced timing closure. So good ideas to step back and exposing you to a whole lot of things that designers need to be aware of when they're trying to close timing. And I talked about it earlier, the hardware debugging techniques where you can actually target hardware residing in Montreal to use ChipScope Pro or Vivado Logic Analyzer and help characterize your gigabit transceivers and characterize the paths of those using hardware as well, using the Serial I/O toolkit. We do a lot of embedded design, and functional verification is a path that is really necessary as we get deeper and deeper into FPGA design and UltraScale, UltraScale Plus, and now into Versal. That functional verification is just critical to making sure that we're advancing properly. So we do teach over 70 courses. This is not exhaustive. This is just showing some of the highlights, some of the more popular courses that are available, and some of the learning paths. So from beginner all the way down through advanced as you work your way through the different paths of what you may be trying to learn. Some of it is dealing strictly with just the architecture. Some of it takes you down design, productivity, essentials, and advanced time enclosure, et cetera, as you work your way through, and getting into that functional verification as well. All right. So that brings us to the end of our story today. I'm hoping everybody enjoyed it. There is some time for a few questions and answers, although if you do have some questions, if we don't have time to get to them now, we will endeavor to get back to you. For those that do have questions or haven't thought of them yet, you can strike out at training@hardent.com, and that will go to the training team, and we'll get back to you in a reasonable amount of time to make sure that you get an answer to your question. All right. So that is the end of this presentation. And I will stop sharing my screen, and I think that they will take it off from the head office. And maybe I need Marianne to come in and tell me what to do.
Hi, Eric. Yep,
Yes.
so we have a few questions from some attendees.
Okay.
If you don't have them there on your screen, then I can read them out to you.
Okay, let me just pop this back up, sorry, so that it's in the middle of nothing at the moment. There we go. All right. So go ahead. If I'm doing the right thing, or do you need me to do something else?
No, that's fine. I can, if you don't see them there, then I can read them to you. So first one comes in. Does the NoC support both memory mapped and streaming AXI interfaces?
Absolutely. So it, for the most part, it's AXI4 for the memory map, but it can also support AXI3 at the memory map side as well, and streaming is AXI4. So absolutely, it supports.
Okay, great. Thank you.
Okay.
And we have another one here. Are there any buffering between master and slave units?
So the buffering is available to be there. Again, it's, you've got these virtual channels that are available to you, and you would be describing what your requirements are. Some of that is through the priorities that we talk about setting. If you're isosynchronous, then you want it to be 36, a latency of 36 each and every time, no matter what. Even if it can get there in 22, it's going to buffer things. So it's either going to hold it back on the transmit side a certain time, or if it gets into the paths, then it can buffer inside of the paths as well, either through these virtual channels or other manners for it to go off and buffer. So yes, it can buffer. The NoC itself can buffer.
Okay, great. Thank you. Have a third question here. Should the DDR be always connected through NoC on this Versal device, or can it be connected directly to
Fabric? So to my knowledge, it can only be connected through the NoC, and the NoC is in every part. So if there's if you're in a Versal ACAP, there is a NoC associated to it. So can it be accessed? You're going to have to talk to Xilinx, because I've not seen anything that tells me one way or the other whether it can or cannot be accessed. I've only learned that the way to access it is to go off through the NoC to go and do that. So again, talk to your local Xilinx rep. I've not been made aware. I don't have that many people I can talk to from that perspective to go off and get this information. Based on lockdown in Ontario and all kinds of things, I don't get too far to be able to talk to people that have great experience, right, at Xilinx with respect to what's been developed and designed in this tremendous technology that they've put out. Go ahead, Marianne.
Okay, thanks.
No problem. We're almost at the top of the hour, so let's make this our last question. Anything else, we will endeavor to answer back by email at that point.
Okay, sounds good. So we'll take this as the last one.
Yep.
What's the purpose of the NoC_TG? How do you configure it, and why is it necessary in conjunction with the NoC?
So it's not necessary in conjunction with the NoC. It is just a piece of IP that's fully available and easily manipulated to put down into the BD. So it might be your own piece of IP. It could be some other block that you used IP catalog to go off and create. It is just, this design was just fairly simplistic in that it was a traffic generator. That's the TG. It's just a couple of traffic generators for that matter that go off and put some data in the block RAM. From that block RAM, it probably goes out the other side into the regular IO and talks to the outside world or gets used in some other manner. So this is the design that was just put forward as a demonstration at that point. The traffic generators, are quite complex in what's brought together. And Xilinx offers these non-proprietary traffic generators that are, as you saw, very easy to create an IP integrator. You can make whatever changes, so you could open up, as you can any other IP in the IP catalog. You can double click on it, open it up, and make whatever specifics you want to, changes you want to make that are available to you out of the core itself. So highly variable, just like most other things are inside of Xilinx. It is not a hard macro that's being used at that point. It is a macro that's built using the general fabric, but there's many other macros like PCI Express, etc., that are fully available to you, as well as C6 and other Macs. Other macros that are there, just like the NoC, built directly into the fabric, into the silicon, that are highly flexible in the way that you can go off and use them as well. So I hope that answers the question. All right, and that takes us just a little bit over the hour.
Yep, nope, that's perfect. So thanks very much, Rick, for a wonderful presentation and for answering those questions. And I want to thank everyone for attending. And we hope to see you all again soon at another one of our events. Thanks, everyone.
Thank you very much, everybody.